All right, polynomial of degree 6 would mean that the tails would go the same direction. That's essentially what we would know. Now, it wouldn't have to have 5 humps, but it could have as many as 5 humps in polynomial. Polynomial is always going to be nice and smooth. Odd degree is going to go opposite directions, tails, and an even degree is going to be like this. So it'll either go up or it'll flip down. It's got a negative leading coefficient. So on D, it says, is it possible that there are no roots? Real roots, like real numbers. Anybody remember in algebra we talked about complex numbers? Yes. Right there. Right? Roots is where it crosses the x-axis, right? That's one of the things we're going to be talking about on our calculators today. So it's possible that it will never cross the x-axis. No real roots. Now, one of the things you learned in algebra was that a polynomial of degree 6 will always have 6 complex roots. And complex means the imaginary numbers and the real numbers. Remember I, right? Square root of -1, which is I. So if you had a polynomial like this, then there'd be no real roots and all 6 roots would be complex. Okay? But we will not really do much with the complex numbers at all here in the calculus that we do, so we don't really need to worry about that. So no real roots. So the next one says, is it possible that q of x is less than or equal to 11 for all x? Is it 11? Is that what it said? Yeah. Is it possible that q of x is less than or equal to 11 for all x? Is that possible? What do we think of on q of x?
No.
Well,
X.
what does this mean, q of x?
Q of X is Y.
The y values, the outputs. Is it possible that the y values are all less than or equal to 11?
Yes.
Sure. If we just took this thing and moved it down here, those y values would all be less than 11. Okay? For all x. In other words, right, the domain is all reals, right? So for all x inputs, the y's would all be less than 11. Then they put bars around for the last part. What does that mean? Well, right, but I mean, what's that mean for the y values then?
No, it's saying that
Well,
can you make it not cross the line of 11, the negative 11, or the positive 11?
right. Yeah, I know absolute value makes this positive, but yeah, what it's saying is, could you have a function that where all of the y values, when you made them positive, would all be less than 11? Well, what that means is, if this is 11 here, you have to think about what about the negative y values, right? So if I took, well, there's a couple ways to think about it. There's one way I want to kind of go with what Jared was saying there, is just kind of think it through, okay? So is it possible that all the y values, that when I turn them to positive, they're going to be less than 11? Well, if I have a function that's, how are they going to be less than 11? Well, they'd have to be down here, but the tails can't go up, right? Because that would be greater than 11. So that's no good. So the tails are going to have to go down, right? Like that. But eventually they're going to get down here, right? And if they get down here, they'd be like -12, -13, -14, which when you do the absolute value would make them greater than 11, not less than. So is it possible? No. Now, what I'd really like for you to see when you read this is the other part of what Jared was saying, which is that. That's what's really happening here. Okay? When you see absolute value has to be less than 11, well, yeah, less than 11 is all these numbers down here, and all these numbers down here are less than 11, but once you get past -11, now the absolute value is bigger than 11. So this is a shortcut way of saying this. Okay? So all the y values have to be between -11 and 11, and that can't happen. That cannot happen because the tails have to go all the way up to infinity or all the way down to -infinity. So that is impossible. All right. What else was on there? 19? Was that another one? What was 19 all about? Not too many questions on 19. Tangent. Anybody, what was the part of 19? This just has to do with the old tangent graph, right? What's the basic, we're not going to do a lot with tangent, but tangent goes through like so, and it's got asymptotes. Where are the asymptotes here?
Pi halves.
Pi halves, negative pi halves, and then it goes every pi, so the next set of asymptotes is going to be at 3 pi halves, and then it crosses right here at pi. Kind of looks like a cubic kind of a graph, but it's, okay? So, is it periodic? Yes, it's a period of pi. Domain is everything but, how would you write the domain?
Put all real such that x is not equal to pi halves, 3 pi halves, 5 pi halves.
Dot, dot, dot. Yeah.
Yeah.
All reals, x does not equal pi halves, 3 pi halves, dot, 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 and actually go the other way too, right? The negatives. Remember what?
Plus or minus one over pi.
Yeah. Remember the that notation? We're going to use that here a little bit today. Remember when you'd add a 2 pi n or a pi n when you were solving trig equations, right? N is any integer, right? Like 1 or -1, multiples of pi. So pi halves, and then another pi, and another pi, and another pi, and another pi, and you just keep adding pi's. Or it could be negative, so that would take care of the ones this way. So x cannot equal that, but anything else it could. So that'd be a good way to write that. The range, of course, is all reals, because that's the y's. C is interesting. Tangent is sine over cosine, right? We all remember that? Now, but what do they mean by use the properties of sine and cosine to show that tangent is odd? What do we say about sine? Odd or even?
Sine is odd.
Sine is odd. Sine has origin symmetry. Remember what origin symmetry means is if you put in opposites, you get out opposites. That's what origin symmetry means. That's what an odd function looks like. Okay? Cosine is even, which means if you put opposites in, you get equal out. The same thing out. This is what we would want to use to show this. So if tangent is this, then what if you put the opposite into tangent? Right? If you put a negative x in, that's like putting a negative x in there. Correct? And what did we just say you would get out of sine if you put in opposites? You get out the opposite. You get out negative sine x. And what would you get with cosine? The same. So, if you put an opposite into tangent, what do you get out? An opposite, right? Instead of sine over cosine, you get negative sine over cosine. So opposite in, we got opposite out, it's got to be what? An odd function. It's got to be an odd function. Now, we can tell by looking at it here that it's got this origin symmetry, right? You put in this, you get out that. You put in opposite, you get out opposite. That's another way visually you can see opposite in, opposite out. Go this way, you go up. Go this way, you go down. Okay, that's opposite in, opposite out. Another good way to show that. Just like here, even function, you go this way, go up. Go that way, also go up. Same amount. That's an even function. That's y-axis symmetry. Okay? All right, so that's a good discussion one there with odd and even. Where is f increasing? Now, so this was just some stuff about increasing and decreasing. Well, this function's always increasing, right? So 0 to 2 pi, you would say from 0 to 2 pi, you say, well, it's increasing from 0 to pi halves, right? It doesn't exist at pi halves, so we wouldn't include it. So it's increasing 0 to pi halves, then it's increasing from pi halves to 3 pi halves, and then it's increasing from 3 pi halves to 2 pi. So just notation-wise, understanding that, I would write that this way. I'd say it's increasing from 0 to pi halves, it's increasing from pi halves to 3 pi halves, it's increasing from 3 pi halves to 2 pi. I think that's a good way to say that, right? That's where it's increasing. Now our next quiz, not the one tomorrow, but our next quiz, we'll be doing a lot of stuff like that, intervals of increasing and decreasing and concavity and local max and min. Are there any max and mins? Local max mins on tangent? No, right? Local max mins, remember those peaks, right? Peaks and valleys. And there isn't any of those. Concave up, it's concave up when it switches right here when it goes above the x-axis. That's concave up, right? It's concave down here, switches to concave up. So from 0 to pi halves it'd be concave up. From, what's this?
Pi.
Pi to 3 pi halves would be concave up, right? And then that'd be it, right? From 0 to 2 pi. Inflection points are there at the intersection, so at 0, at pi, at 2 pi would be inflection points. Probably wouldn't, but to be honest, if we're really going to be technical about it in H, are there inflection points? Where are the inflection points from 0 to 2 pi? Would you give 0 as an answer? Because in their directions, they didn't include 0 and 2 pi, did they? Right? They had the parentheses, not the square bracket, so you really shouldn't say 0. You really shouldn't say 2 pi. You should really only say pi is where you'd have an inflection point. Remember, inflection point is where the concavity changes. Okay, any roots? Same answer, right? Pi. And vertical asymptotes, 3 pi halves. Okay. What else was there? 18, 31, and then of course that 47 through 49. Okay. 18. Okay, yeah, there was something about that. I wanted to talk about that 2 pi in there. When we were doing that IXL the other day, what did we say would happen with the 2 pi? Now I know you probably remember something from last year, but forget the trig part of it. What did we say with a number on the inside multiplied? What's that do? Shrink. If the number is bigger than 1, it's a shrink. If it's less than 1, stretch. It's the opposite. When it's on the inside, it's the opposite of what you would think. So a plus is actually a left and a minus is right. A bigger number in here is actually a shrink and a smaller number is actually a stretch. So this is a shrink by what factor? 2 pi. So what we said is, so the example we gave is, okay, if there was just a 2 in there and you had a point out here 6 units out, where would it be in the new graph? If there's just a 2 in there.
3.
It'd be at 3. 6 divided by 2, right? Well, on the sine graph, the one I'm going to pick, because it wants to know the period, I'm jumping ahead here a little bit, I know there's a point out here that the 1 period I know is at 2 pi. Well, my new graph, where's that going to be? At 1. It's going to be at 2 pi divided by 2 pi, which is 1. So that means on my new graph, when I go here to here like that, that's actually going to be at 1, which of course is way in here somewhere, right? So it's going to be shrunk, compressed in. Now you might remember that last year. Isn't that what you did with numbers that were inside? You took the normal period, 2 pi, and divided by that number, right? But what I'd rather you know is just in general, when you have a number multiplied on the inside, it's going to shrink or stretch by that factor. So just take that important point, which is 1 period, and just compress it by that factor, 2 pi divided by that, whatever that number is. Okay? All right, what other parts of that one were tricky on 18? Local max and min's pretty easy. Concave up, concave down's pretty easy, I would think. Inflection points. Now they said from 0 to 3 a lot in that question. Well, isn't that going to be 3 whole periods? Once you figure out that the period is 1, you're going to have 3 full cycles of that graph to answer those questions on. So if this is 1, what's this point? 1/2. What's this point? 1/4. And then this one? 3/4, right? So when you start answering those questions about where are the local max, like there's a local max right there at 1/4, there's a local min at 3/4, right? That kind of thing. On the quiz, I'm probably not going to ask you one like this with, well, I take it back. I've already told you, I may ask you one like this, but I've already told you get to use your calculators, right? So, and maybe you did on the homework, so that's why a lot of you didn't have a question. Notice I've been doing all these without the calculator, right? And we do want to be able to do that. All of what I've been doing here, we want to be able to understand without a calculator. We need to know those, okay? I'm just not going to make you do that on this quiz, okay? You'll have your calculator, so be able to trace and find those values and that kind of thing, which we're going to do here in a minute when we review a little bit with the calculators. Okay, so let's go to 31. 31 said ln of x cubed plus 1. Now again, if you graph this on your calculator, and let's have a volunteer here. Andy, did you get on yet?
I don't have a network.
Still not. Jasmine, you either? Okay. Huh. Blair, you're up. All right. Get on the graph screen. Let's put in ln. Oh, good job. Way to go. Got it up there already. Okay. Now, let me show you something. Do they give us an interval here? They do not, do they? Okay. Let's say, let me just show you this real quick. On the quiz, I want you to be able to get on your calculator, put in a graph, trace on it, look on it, and be able to set a window as well. Now, you may have to set your own window based on, and by the way, make sure you charge up your calculators tonight, okay, so they're ready to go tomorrow. But be able to trace and set a window and all that stuff, and also know enough about domain and range, those kind of things, that you may have to set your own window. Now, I may tell you, I may say x is between here and here, y is between here and here, and help you out that way. It depends. Maybe one problem I might, another problem I might not, okay? Sometimes you only have the x window. So let's say they wanted us to look at this graph from -3 to 3. That's it. So everybody go on your calculator here, go to the window. So under menu, window settings, what I say, -3 to 3. So put in -3 for the x, 3 for the x max. Now, here's what you do if they only give you the x. The first thing I would always try. So hit OK, just hit OK. Now, that might be good enough, right? But it may not show everything because you haven't set the y values. So go back to the menu and window and scroll down to, not window settings, escape out of that. So go to menu, window, and then down to A, zoom fit. Zoom fit is a good one to remember. Because often we're given a domain to work with on a graph, but not a range. So you set the x min and max first that they give you, and then you go to zoom fit. And what that does, that zoom fit? That zoom fit? Oh, I'm surprised a little bit. I thought, oh, okay, well that's fine. That's good. It's actually good. Because what it usually will do is it will find, oh yeah, of course that is why. I know why I did it. So what it'll do is it'll check from -3 to 3, it'll check all the y values, it'll find the biggest y value, the littlest y value, and it'll set your window to that. Now we actually have a vertical asymptote right here at -1, right? Because think about it, if you put -1 into this, -1 cubed is -1 plus 1 is 0. You can't do natural log of 0. Remember, the domain of natural log is just from 0 to infinity. Just positives is all you can put into a natural log. So anything past here is going to be negative inside there. So there's no values here. So it goes way, 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 way down. It's good that it didn't set the y minimum at a really huge, silly number for us. So that's kind of smart of it to do. So it sets your window so you can see. Is everybody else getting something pretty close to that? Right? Same thing? Okay. So that's a good thing to do. All right. Now, what they want us to do here. Find the domain and the range. So graphing it, I think, is a good way to do domain and range on a function like that. So it looks like the domain is from where to where?
-1 to infinity.
Looks like -1 to infinity. Now we set it at a small window here. We can zoom out on this thing. Matter of fact, let me show you the zoom. So go to menu. Here's another thing you can do to experiment with the graph a little bit. Go to window, go to zoom out. Okay, it's going to ask you where do you want your center to be when you zoom out. So I usually, right in the middle is usually a pretty good spot. So you kind of move with your thumb or your finger on the trackpad and hit the middle of it, or hit enter. Either way I think works. Okay, and then do it again. Okay, and do it again. And you kind of start to get a pretty good idea of what's going on here. The normal natural log just kind of levels off as you get out here, just kind of levels off. But it doesn't ever really level off. It's always going up, just very, very slowly. But it's getting really, really close to horizontal. Okay, and let's do that in reverse. Let's say you had done a graph like this, and go ahead and move your magnifying glass here a little bit. And so you do, and you see, there's something going on here. Right in here, it seems to be kind of, I wonder what's going on, if there goes up and down a little bit or what happens. So you might want to zoom in on a graph. So go to menu, and of course you can always zoom in by just changing your X and Y numbers. But go to menu, window, zoom in, and then get there and just hit enter, or hit the middle of your trackpad a couple times. Zoom in, right? Maybe even zoom in a little more. And then, and again, and that's good enough. And now, yeah, it looks like it just kind of like a cubic. It just kind of flattens and then kind of goes up again. Kind of an inflection point, concave down, and it looks like it switches to concave up. Now, as flat as that looks, it's probably not flapping. It's probably going up. If we trace, go ahead and hit trace. Let's investigate that real quick. So our domain looks like it's going to be -1 to infinity. And our range looks like it's going to be -infinity to infinity, right? Because it goes all the way down their vertical asymptote, and it's going up, but just very gradually, but it's going to keep going up. So the y values are going to be -infinity to infinity. So trace to the left. Do you see how those y values are negative? So even though right here it looks like it's horizontal, it's really not horizontal. It's still, it's below, and it's just creeping up, creeping up, creeping up. Keep arrow back to the right again. Okay, 0. Now go to the right. Now it's positive, right? And so it just crosses right at that one place. There's 1 0. And again, your calculator is going to find those zeros and stuff for you. One of the things you're going to do on today's homework is trace and find some zeros, some roots. But it's easy. You just trace about where you think it is. The calculator will find it for you automatically. Same thing with maximums and minimums. Okay? All right. 47 through 49. Let's talk about those. All right. So, I think we talked about this a little bit when we were doing the IXL. So if I've got a horizontal asymptote of y equals 2, okay, right up here, and I take a function in part A and shift it up 3, where's my horizontal asymptote now? Oops. Isn't it a y equals 5?
Yeah.
That's what that's saying. See, it says y equals 2 is a horizontal asymptote of function f. Y is y. Oh, duh, they said. I'm sorry, you're supposed to explain. Explain why y equals 5 is a horizontal asymptote of g of x equals f of x plus 3. G of x equals f of x plus 3 takes the f graph, adds 3. Takes the f graph, shifts up 3. So the horizontal asymptote will shift up. Because think about what's happening. If you got a horizontal asymptote, it means this is coming in here, getting close to that value. Well, if all the y values are now, you add 3 to them, they're all going to be up here, leveling off, right near 5. So the horizontal asymptote goes to 5. Okay, what's a horizontal asymptote if you shift it left 1?
Still going to be 2.
Still y equals 2. What if you, wow, what are we doing here? Well, we're doing 3 things. Let's start on the inside. So the first one is left 4.
That's not going to change it.
That's not going to change it, so still be at 2. Then the 3 on the outside is going to what?
Gotcha.
So on the outside,
Let's get a move.
so that's vertical, so that's normal, so that's a stretch. 3. So where is it now? Would it be at 6? Because all these values that are really, really close to 2, like 1.999, are now going to be 3 times that, right? 3 times 1.99999 is 5.99999, right? Almost 6. So it's y equals 6. Then we're going to shift it up 1.
7.
So 7.
So now it's at 7. So the horizontal line is going to be y equals 7. Okay? 48. X equals -3 is a vertical asymptote. And what happens if we shift that graph up 3? Still a vertical asymptote. Part B. What if you go left 1? So now it's x equals -4. And then what if we shift left 4? So where is it now? -7. Then we stretch by a 3 factor vertically. Doesn't change, right? Vertical asymptote still be at -7. And then we go up 1. Doesn't change. Doesn't change. So it'd be at -7. Okay, 49. All right, 49. Oops. Blair, you're up again. So this time let's go into hit your tab and let arrow up and let's delete that out of there. And let's put in that first equation, which is do a fraction, so hit Control Divide, and then do x minus 3 over x squared minus 9. Hit enter. Okay, and then tab again, and then we're going to put your fraction again, Control Divide, and then 1 over x plus 3. All right, let's do it. Now, I'm not sure where to start with this, so we're going to just do a standard window is what I often start with. So let's go to Menu, and let's go to Window, and number 5, Zoom Standard. And that's just kind of the normal thing. And if this is bugging you can grab and what you can do there is you can hover your cursor over the red there, and then if you get that little fist, and then if you click down and hold, it'll close that fist, which means you grabbed it. Now you can move with your trackpad. You can move that up or something if you want. You can just, whoops, now you lost it. Click and hold again. I think you can hit Control too. And now just move, there you go. Now just slide with your finger. It's pretty, there you go. And now let go. There you go. There you go. So if you want to kind of move things out of the way. Now, what does that tell you about those two graphs?
The same.
Looks like it, right? And matter of fact, in Mrs. Andreessen's class, you probably would have said those are the same. She would have said simplify this,
Just factor that.
and you would have factored the bottom, right? Which would have been x plus 3, x minus 3,
And they just cancel.
and you would have canceled,
So it's 1 x plus 3.
and you'd have done this, and you'd have been fine, and she'd have checked it right for you, and away you'd have went, and those two are equal. And you'd say, yeah, they are. Okay, now, show that f is equal to g for all x such that x does not equal plus or minus 3. Oh, interesting. What's wrong if x is plus or minus 3?
Then we divide by 0.
Oh, you're dividing by 0 then, and there's no value. When you divide, if you put a 3 or -3, there's no value, so they can't be equal, right? So there are no outputs there, okay? All right, so, but other than that, so that's how you would show it right there. They're equal, except at those places they don't have value. Okay, that's fine. What's the domain and range of f? So here was f, right? So what's the domain and range? And then this is g over here, basically. This is f. What's the domain and range of f? Domain. What values can you legally plug in?
Negative infinity.
Now what did we just say?
Wait. Time out.
X can't be 3 or
Negative.
negative 3. So I could do this, then this, then this, right? Whoops. Or, if you'd rather just say all reals except, like they did, X can't equal plus or minus 3, I'm okay with that too. All reals except positive and negative 3, whatever. I mean, this would be a way to say it, but this would be a way to say it too, right? I don't care. What about the range? Now, here we got the calculator to help us.
Don't think so. X is not 0.
It looks like everything but a y value of
0.
0. It looks like. Everything but a y value of 0 looks like. Now, that makes sense because if we look at this, it simplifies to this. What's the only way a fraction can be 0?
If 0 is in the top.
If you have,
Numerator.
yeah, like 0 over 3 or 0 over 4 or something like that, right? Well, you're never going to have 0 on top. The only way you can have 0 on top is if x is 3. But the problem with that is
Then X
you
is
get 0 on the bottom, right? You can't have 0 on both the top and the bottom. Now, one of the things we're going to learn later, it's not going to be under quiz or anything, there's a big difference between 3 over 0 and 0 over 0. Or actually, you're going to see it here in about a minute. There's a big difference between 3 over 0 and 0 over 0. They're both undefined, but they're a different sort of undefined. Okay? So anyway, this can never be 0. So we can see in the graph that it's all, the range is everything but 0. So y cannot equal 0, or f of x, you might say, cannot equal 0. Okay, so it's everything but 0. Negative infinity to 0, 0 to infinity, whatever. But then they ask for the domain and range of G. What's the domain of G? This graph.
the same.
No, it's not the same.
Wait.
Can be negative.
It just can't be negative 3.
It just can't be negative 3. It can be positive 3, right? So now, so back in Algebra 2 class, when you were saying that these two are equal, are they really equal? They are not equal. This one, x can be 3. This one, x cannot. Now, what happened? Well, when we canceled, what happened? We took away the thing that was making the bottom be 0 when x was 3. So we eliminated one. Remember the whole thing with extraneous solutions and losing solutions and stuff like that? We're going to talk about that a little bit here with some trig stuff in a little bit too. Right? That's an issue. Now, don't worry about it for the quiz tomorrow. That's not going to be a big deal. But I do want you to be able to graph on a calculator and be able to trace, you know, and see some of these things from that standpoint. All right. And then what's the range?
Everything but 0.
It's the same, right? It's everything but 0. Again, we can't get 0 here, so that part of it's the same. All right, now, we're going to go to the graphs here again in a second. Let me see if I'm leaving anything out. Okay, that's next. How are the graphs related? Well, they look identical. Are they? Now, what did we just say? We said negative 3 is no good on either one of them, right? That's right here. We got a vertical asymptote. Now, go to the original, and let's put in a negative 3. Well, what's negative 3 minus 3?
Negative 6.
And put a negative 3 down here. What do you get?
9.
0. 9 minus 9.
Yeah.
Well, that's no good. That's undefined. Put a negative 3 in this one. Well, 1 over 0. But again, same thing. Undefined. That's bad. Okay? Now, so, and we can clearly see that. Whoops. We can clearly see that on our picture. That you put a negative 3 and that's bad. Right? Matter of fact, Blair, trace there for me. Go to the menu. Go to trace. Type negative 3. Hit enter. And look what happens. Kind of cool. Puts that vertical asymptote, says, hey, that's undefined. You got a problem there. Okay? Now, notice we're on the blue graph right now. Because, right, we're on this one. Now hit the up arrow, Blair, or the down arrow. And now type in, now you notice how we just switched to the red graph? Type in a negative 3 now. And again, undefined, right? Okay. Now, what's the other interesting point in this thing we're talking about here? What's the other x value that's something weird's happening? 3. Type a 3 in right now. Blair, we're on the red graph. Aha! Look at that. We get a value. Well, sure we do. What happens if you put a 3 into the red graph? 1/6. That's what that value is. Hit the up arrow, Blair. And type in a 3. Oh, it's already there, but go ahead. Now, is there a vertical asymptote there? No. Now, it threw this in. That's not really a vertical asymptote. What's happening there? Well, if you were going to draw this graph, what's happening is this. You've got this vertical asymptote here at -3, and then it comes down like so, and right there at 3, you have a hole in the graph.
So it's just going to skip over.
It's just going to skip right over that point. There's a hole. There's just a hole in the graph. Now, so this is in that whole thing about rational functions, when you have a polynomial over a polynomial. So, remember, now again, I'm looking ahead a little bit. This is not important for the quiz. Remember when I said there's a big difference between like 1/0 or 3/0? That's a vertical asymptote. That basically means infinity. What that means is 1 divided by a really tiny number, which is a really big number, right? You divide by a millionth, you get a million, right? So you divide by something, so you got 1 divided by something really tiny, what you have is a vertical asymptote. If you get 0/0, that's a hole in the graph. And that's why at 3, there's a hole. So those graphs are identical except at 3. One, there's a hole, the other one, there's not. And again, why is there not a hole? Because we canceled it out, right? When we simplified, we canceled it out. 3's not a problem anymore after we simplified. Okay. Well, we're going to, like I say, we're going to get into more of that later. But the important things, I think, for tomorrow, for the short term that we've talked about, is this all this graphing stuff. Trace, set in your window, those kind of things. Okay? All right. Let's talk about the quiz a little bit. So if you want to get your notes out, let's just write down some things that I would want you to make sure and know or to focus on for the quiz. Now, very first thing that I told you would be on this quiz would be a piecewise function where you have maybe a circle or you have a line or pieces of lines, pieces of circles, right? And so being able to write a line equation, being able to do that circle problem. We did that, I think it was number 12 in the homework. There was an example in the book that we did in class together. So going back and revisiting that would definitely be time well spent. I pretty much promised you that was going to be on there. Now, also going along with that, I would want you to be able to answer. Well, the other thing that was in section 1.1 was domain and range kind of questions. Now those questions have continued on through sections 2 and 3 as well. So we've done some domain and range with graphs. If you have a graph and be able to look at it, I think that's helpful to do domain and range. So you've got your calculators you can use tomorrow, so you can draw graphs if you need them. But then the other side of that coin would be if I just give you a graph. So for example, if I give you, I think here's the one right there. So what is the domain of that? -5 to 5. We'll assume it doesn't go on to infinity, right? It stops. Anytime you have the grid box in like that, usually, so -5 to 5. Now, if this would have changed, if this would have been maybe here, this just had an open circle right there, and then this piece wasn't even there, then you would go -5 to 0, not include the 0, and then 2
to 5.
to 5, that kind of thing, okay? So anyway, so on a piecewise, we can write the domain just by looking at the graph and as well. What about the range?
-4 to 2. -4 to +2.
-4 to +2 inclusive, right? There's no gaps in there. It hits some of these y values more than once, which is fine. -4 to 2 would be a range. Now, it's possible then that we had another chunk up here or something, you know, there could be some gaps in that, right? And so you just kind of start with the lowest and work your way up. And there might be some gaps, but this one, it would just go -4 to 2. Okay. Yes?
So let's say like we have a hole at 0, 3, and like there's a point at 3 and like say 4.
So I'm not following where you're
So
going.
at like 0, 3, let's say there's a hole there.
Right here?
Or 3, 0, excuse me.
At 3, 0.
0.
Right here?
Yeah, and then there's like a point above or below that. Like
Yes.
it's outside of the range. Would that change what the range of the...
Very good. I wanted to do an example, but it would have to pass the vertical line test, right? Well, this would do it, right?
Yeah.
So let's say we had a hole here and just a dot up here. So what about the domain? Did that change the domain?
No.
The domain's good, right? Now, if there wasn't a hole here, right? Or excuse me, if there wasn't a dot up here, what's a domain?
-5 to...
-5 to, even though there's a hole there, we don't care because there's a dot there.
Not
-5 to 3, then 3 to 5, right? Not including 3. So there's no output at 3 if there was a hole there, right? No circle. But then if we did have this, now what's your range? -4, whoops, -4,
to 2.
this hole and this hole don't matter because right there is a y value at 0, right? So -4 to 2, and then 4. How would you write that?
Okay.
4 or x, no, not x. Y equals 4, you could say that. But if you just want to show a 4, you could just do that. Yeah, good example. And so that's where there's a kind of a gap there. Yeah, that's what you would do for the range on that one. Okay, so be able to do domain and range, piecewise, that kind of stuff, but also the domain and range that we did on our calculator. So that was basically 1.1. Okay, 1.2 is where we really focused on graphs, and that's when we hit even and odd and periodic. So really looking over those things. We already talked about even odd a little bit today. We talked about periodic, that repeating. You had those examples where if you move over 7 units or multiples of 7, they have the same output. Be able to answer those kind of questions about that. That means you get the same output out. So look over that set of exercises you had. I don't really have it. One thing about this book, we don't typically have like review exercises we go over. You know, it's more like, okay, go back and look at those homework problems you had. Sometimes we do. Sometimes we try to come up with some of those things and so forth. But it's more a matter of just going over it. And here's where it is. And that's pretty typical in a college type of setting as well. But even odd, we talked about that, opposites in, the symmetry that you have, those kind of issues. Again, since you have your calculators, you're going to be able to look at a graph and tell if it's even or odd. We had that problem today where we talked about the tangent. That was a good example. I mean, there might, like I was saying a while back, one of the things about the quiz is typically is you're going to see plenty of problems that feel like they were similar to homework problems, but there's going to be some that maybe stretch you a little beyond. Take the concepts we've talked about, but maybe it's a different kind of problem than you've seen, you know. But if you got the concept of what's happening, you know, you should be able to apply it in that situation. Well, was an example of that. Use sine and cosine to show that tangent is odd. Okay, well, we took this notation we had used with even and odd, and we kind of applied it. You put opposites in, you know, and write it that way. So, again, that's just an example. I would think that was a question that was a little beyond maybe some of the other types of things we did with even odd. But basically the symmetry and those kind of things, knowing that. All right? Of course, we did have a lot of talk in there, in this section also about local max min, a lot of vocab, I guess terminology I might just put in there. If you're going to look back through that, local max min, inflection point, concave up, concave down, those kind of things. Those are going to be really more important in our next quiz. But maybe I want you to trace to a maximum point or something like that. Pretty easy terminology, really. So some of that could be in there. And then section 3, section 3 was just these different function families. So an exponential graph and polynomial graphs and trig graphs. We did the thing with rational functions where there's some asymptotes. But again, you get to use your calculator for those. So if I give you a trig kind of thing, you can graph it, you can look at it, but just understand that we need to kind of know what the basic shapes of these things are so that we can work with them. Okay, so you had some domain range questions in there today, some even odd, all that stuff that was in those earlier sections we applied to these different types of functions, so nothing really there. But I would say, and then this is kind of overall, that be able to use your calculator, okay, be able to use your calculator to draw a graph, set a window, trace, those kind of things, and just read graphs in general. Be able to read from a graph. I give you a situation like in the homework in section 2 we talked about. Give you a situation where the y's mean this, the x's mean this, and be able to read and understand what those things do. Okay, so that's pretty much it. That's what I want you to be able to do for the quiz. All right. So we're going to just quickly do a trig thing. I'm going to give you basically an assignment on solving trig equations. It's more practice than anything. This is, again, something that as we get into our next couple quizzes, you're going to have to be able to do, not for tomorrow. So we're kind of done. Now we'll put that aside a little bit for tomorrow's quiz. When I give you some work time, you can do whatever. You can review for the quiz and look over that stuff if you'd rather, or you can work on this trig stuff, okay? And then the assignment, this assignment is kind of really for Wednesday then. Okay, I'm not going to come around and check it tomorrow. So your focus is to get ready for the quiz, and then after the quiz, I might add a little more to it, but this is for Wednesday. So if we have this problem right here, we're just going to do one together here. Now we really want to be able to solve any kind of equation, but we've already done some work on exponential and log equations and polynomial equations with factoring and stuff we should be pretty good at. You've practiced that a lot. So that really leaves us the trig ones to focus on. So let's say you had this right here and you're supposed to solve it. Thoughts on the first thing you might try?
Get rid of the root 3.
No, that's logs. You're thinking of logs.
Get rid of the root 3.
What do you mean get rid of the root 3?
Divide both sides by root 3 or negative.
I don't think I'd do that yet.
Multiply both sides by 3.
Multiply both sides by root 3?
Or divide by 2, because then you'll have
2, which can be changed.
Okay, root 3 over 2 is a number that whenever I'm doing trig, 1/2, root 3 over 2, root 2 over 2, those are numbers I'm looking for, right? And I remember that, hopefully I remember root 2 over 2 comes from this, actually, a lot of times, okay? And if tangent's ever involved, then root 3 is a number you like, and root 3 over 3 are numbers that come up a number of times, okay? And root 3 over 3 comes from 1 over root 3. But anyway, those are numbers, so I see that in there, but you guys are all missing the first step. Now, a lot of times people want, I worded it this way on purpose, a lot of people want to divide by sign right away. Now, the problem with doing that is you lose solutions, right? Because you can't divide by 0. And can sine x ever equal 0? Sure. right? At 0, at pi, at 2 pi, right? Sine can be 0. So we don't want to divide by 0, so dividing by an x is usually bad. So what's the other option? There we go. Let's add this over to this side. So what we want to do is, and isn't that a pretty common strategy? Get 0 on one side? That is a real common strategy. Get 0 on one side of the equation. So here's what we want to do here. Because now what can we do?
Now, oh yeah, we can set both of those.
Not yet.
You can complete the square.
No. I thought I could have sworn somebody said it. It starts with an F.
Back
Factor out
the sine.
sine. And then we get 2 sine plus root 3. There you go. The whole reason, listen, the whole reason for wanting to have 0 on one side is because of the zero product property, which is, but product's the key, right? It can't be a plus, it's got to be a product. And that's what happens when you factor. When you factor, you turn it into a product. Okay, so factoring is what we want to do. Now, we can set each one of those equal to 0. So now, either sine of x equals 0, which is the solution we would have lost if we would have divided by sine, and then set this equal to 0. Well, there's nothing to do on this one, so I'll come back to it. Here we would subtract root 3, then divide by 2, right? So now we need to solve each of those. Now, where does sine equal 0? Let's think of the unit circle. Sine is the y, not pi halves.
0, 2 pi.
At 0, pi, 2 pi, 3 pi. Oh, wait a minute. So now the question is, am I asking you to solve from 0 to 2 pi? A lot of times they include the 0 but not the 2 pi, right? Or is it just in general? Well, let's pretend I hadn't given you this. Then it would be 0 plus pi n. So 0, pi, 2 pi, 3 pi, 4 pi, and of course you wouldn't need the 0, so you could just say pi n. If I had said 0 to 2 pi, yes?
I got to
So if I had said 0 to 2 pi, what would you have put?
0 pi 2 pi. Or no.
0 pi.
0 and pi, right? If I don't include the 2 pi. Okay, let's go over to this one. Negative root 3 over 2. When does sine negative root 3 over 2?
Pi thirds.
That's pi thirds. Now, I don't know how you want to remember it, but sine is the y. Negative root 3 over 2 is negative 0.866. I put it in the wrong place, so isn't it? It's negative, so it's not in quadrant 1, is it? But that's bigger than 1/2. 1/2's down here, but so it's actually down here
Yeah.
and down here. It's pi thirds reference angle. So what would that be? So ignore that. So all the way around here in quadrant 3 would be what?
5
5
thirds and 4.
7.
So,
And 7.
that's 7. Okay.
Pi thirds.
Maybe 4 pi.
The first one is 4 pi thirds,
Yeah.
right? Because we got 3 pi thirds around to here, which is pi, and then another pi third. So 3 pi thirds plus 1 pi third is 4 pi thirds. Okay? And then the other one is 5 pi thirds. Because if you go all the way around to here, that'd be 6 pi thirds is 2 pi, but we're pi thirds short of that, so 6 pi thirds minus a pi third would be 5 pi thirds. So those would be the two if we're going to limit it. If we're not going to limit it, 4 pi thirds plus 2 pi n and 5 pi thirds plus 2 pi n, because it'll go around and around and around for multiple solutions. Every 2 pi it'll go around again. All right, so those are our solutions. If we're going to limit it 0 to 2 pi, then there would be those 4 things. Right? All right, You're not going to have to do that tomorrow on tomorrow's quiz, but one of the things one of the things you could do if you had a calculator. Now I'll tell you the calculator will just solve this, but I don't want to get into that and confuse you with more calculator stuff right now. Also, you could graph this. Another good strategy for getting 0 on one side is you could just type that in and graph it and then see where it crosses the x-axis, right? Because where this is 0 is where it would cross the x-axis. And what we find is from 0 to 2 pi, it would cross at 0, at pi, at 4 pi thirds, at 5 pi thirds. That's where it would cross. So there are all kinds of ways with a calculator to solve it, but what we really need to practice is the no calculator part, because there is definitely on the AP test, there's an expectation that you can solve these trig equations without a calculator too. Okay, so I just think we need to do a little more practice with those. There was an IXL one on solving trig equations, so maybe you did that. So I've got a little worksheet, it's got about 8 problems on it is all that you can practice with 4 of them. They don't limit the domain to 0 to 2 pi, and on 4 of them they do. There's a little bit of factoring involved on some. Thank you. There's even a couple of examples worked out there for you. And then the other part of it is Appendix F, but I'm going to change a little bit of that. Now again, this is for Wednesday, really, is when this is. 17 through 32 on Appendix F. I think on the assignment sheet I had a little more than that. I had, through 34. I'm sorry, 34. I had 9 through 34. We're just going to do 17 through 34 with just a little bit of practice on some trig identities and again, just some trig values that you should know. So those should all be tried to be done without a calculator on that Appendix F. Okay. All right, so the rest of the time is yours to kind of review for the quiz, look back that stuff, ask me questions if you need to, and then work on this trig.
You missed everything.